Okay, go ahead and get started. It's great to have Dr. David Redden as our speaker today. I've seen some of you here before, so know that Dr. Redden is chair of the Department of Biostatistics. He's a really devoted teacher and also has a very active research program. He's particularly interested in the way in which tuberculosis spreads and how you organize multi-center clinical trial and research trials, and has a lot of studies involving different aspects of cancer and biology. But he's particularly great at explaining basic fundamental concepts, and today he's going to talk about statistical power. And hope you'll keep an eye out for other talks that he gives. I think he's still going to have his 3-day series or 3 2-hour session series held in trials later in the year, so keep an eye out for that. It's really a fantastic opportunity to get a good foundation of biostatistics.
All right. So first thing I can promise you, and you that have already seen the slides know this, I am not going to bury you with statistical formula, because that's not what I'm looking to do at all. What I really want to do is to be able to get you set up so that if you needed to consult with a statistician, you understand what key pieces we're going to need before we can go. And I also want to put you kind of at rest about something. Always remember this, and you'll see a slide about this over and over. The statistical power section is never the most important part of it. A lot of time I get people, I'm not joking, will stop me on the street and start talking to me about, hey, can you tell me what to do with this power calculation? And I have to turn around and say, slow down. We've got to start somewhere else, because I can't discuss power until I understand your hypothesis. And you'll understand why that's the case in just a minute. The other thing I want you to emphasize is that I am a member of the Biostatistics and Epidemiology and Research Design unit within the CCTS. And I'll tell you again at the end, but we do have weekly sessions where you can come in and just meet with the methodologist, and if you're dealing with a power calculation, it's a straight in. We can judge how complex it is, but if it's a straightforward standard power calculation, we can sit down as long as we bring the specific names, knock that out with you, and help you write it in a manner that should greatly strengthen the application or the grant. All right, so I'm going to talk to you about what statistical power is, and then specifically what it is not, because I think there's a lot of confusion about what it is, and some people want it to be something it can never be, okay? How to approach power calculation, I kind of mentioned a little bit for either a grant application or for a dissertation. A lot of times dissertations come in and we need to look and be able to say, they're going to try to publish this research, what is the statistical power, and it's very common actually for reviewers to come back after a study has been submitted and say, hey, can you show us the power calculation? I have extremely mixed feelings about that. I will explain that in a moment, okay? Because at that point, the question may not even make sense. And I'm going to talk about the statistical concepts that guide the calculation. And as in with any presentation, any PowerPoint set, there is going to be what is called the money slide, the one slide that I have to stop and explain in detail. If you hold on to anything from this, hold on to the money slide, because the money slide will always help you understand what the statisticians are talking about when we go about calculating power. Okay? I'm going to do it by also today, Dr. Chaplin brought up that we have done long series. We do every now and then we'll roll out a 3-month, series of short courses, but symposium, where we go through what we'll do is we'll roll them out and we'll go into 1 month, probably run in January, doing a lot of 2 sample designs. Then we'll run into the next one, how to do multi-group designs, and regression. And then we'll turn back around and talk about what we need to be talking about with regard to if we're doing statistical genetics and power calculations. Because those are because power covers a large section. So today I'm mainly going to do two group comparisons, one dealing with a mean. This is a teaching example. If we're comparing two means, we could be measuring BMIs, we could be measuring blood pressures, cholesterol, any of those things. If we wanted to compare between two groups, what would we have to do? Then we talk about proportions. I'm going to tell you that proportions are always, when people come to me and say, hey, David, I really want to do a two-group design on proportions, I go, my day's easy. Because it's not very hard to do that calculation. There are fewer assumptions there. And I won't be able to emphasize to you how we have to detail the assumptions in the calculation, reveal the assumptions, because somebody's going to review it. And as they review it, if you don't put all the assumptions there, they don't think it was done right. And that's the Achilles heel, especially going to study section. If someone for a second believes it wasn't done right, then they start getting very critical. If it's written in a specific form, and I mean this, by a specific way, they're going to recognize, wait, those are the fingerprints of a methodologist, or that's the fingerprints of a statistician. So they become much more convinced that all the I's were dotted, all the T's were crossed. And as long as they have all the information, they can replicate it. They can come back and do it. And I'm going to say it over and over. Why the most important part of the power section is not the calculation. It's actually the details to replicate the calculation. I do want to emphasize, what is it? Now notice this is not a statistical description. I could give you the gory details and the pure statistical theory definition of what it is. Nobody wants that, not even me. The question I have for you, what do you think statistical power is? When someone does a power calculation, what is it? Been doing it for 21 years, I can stand here in silence for a little bit. What is statistical power? Anybody? Give it a shot. Go right ahead.
The number of samples you need in the two different groups to show that there is a difference.
Okay, I'm going to strengthen that a little bit. You've gone from the first approach. That's a sample size calculation. And when people use the word power calculation, sometimes they mean power, sometimes they mean sample size. Now, what I would emphasize there is that it is true. It is the number of observations needed to have a certain chance of declaring a clinically relevant difference. In other words, I don't want it to be based on data. I want your scientific opinion. But I want to be able to have a reasonable statistical chance of declaring a clinically relevant difference as detected. It has been detected. Notice I have avoided the word significance like because I do not like the term statistical significance. Okay? Why not?
Yeah.
Why not? Because it confuses people. Because I'm more worried about clinical relevance, and just because I got a p-value below 0.05 doesn't mean it's significant in the dictionary term. Could be that I've got such a large sample that I'm finding something that's very, very small, and it's not relevant, but it's statistically significant. Sometimes I have a small sample and I see a big gap, but I can't get the p-value below 0.05 because it's a small sample. But that big gap could still be considered clinically relevant. That's why I'm careful with that word. Please understand, it is a description. Always think about the power calculation is not really a calculation, it is a description of the possible experimental outcomes for which we are likely to declare that the intervention or experiment worked. We're just using statistics. We're using hypothesis tests to try to understand Have we seen something? Okay? And by saying describing the outcome, I'm trying to say how likely are you to be able to declare the outcomes achieved the level you wanted using statistical methods. That's it. Nothing more complex than that. Power calculations. First, I'm going to report a power calculation above 1. Okay? Power is a probability. So your power, well, could be a trick question. I won't do this to you. Your power is actually trapped between 1 and your significance level. I'll explain that to you in just a second. Whatever alpha level you use, as long as the test is correct, you're trapped between that level and 1 for power. Or it can be written as a description of the sample sizes, as you indicated, needed so that we are likely to declare that experiment intervention had a clinically meaningful effect. That's the biggest piece you have to bring to the table for me. On the day you want to sit down with a pop and say, let's, David, turn the computers on, I want to work on sample size and power. The very first thing I've got to know is, please help me understand your experiment. Is it 2 groups? Is it 3 groups? What type of outcome do you have? Are we measuring something that's continuous? Is something like DMI, something that I can take a ruler to, and if I have a really good ruler, I can get really, really fine? Or am I talking about presence, absence? Yes, no. These things drive everything about the power calculation. Okay, what it is not. Please, it is not the first thing to be worried about. I promise you, it is not where you start. If you start, it would be equivalent to allowing the tail to wag the dog. Okay? Don't start there. Always start with your specific aims. That even if you're not certain what you think the clinically relevant difference is, come on and meet with a statistician. That's great. Or a methodologist. That's great. If you don't have the specific aims listed out, or the design, or the outcome, or what you're going to measure, you're coming too early. That, because remember, here's not a stats kind. I know it's outside probability and statistics. I will teach you grantsmanship. You win or lose page 1. Stats are never on page 1. You win or lose a grant with regard to the specific aims page. Always. I've been doing it for years. I've been in study session. I can guarantee you, if they understand the relevance and the way the design is laid out, the stats and power calculations can help you get a stronger score. But I've never had a grant funded that said, we don't believe in these specific aims. But boy, that was a great power calculation. Doesn't happen. Okay? It will not happen. It's not a guarantee of success. Okay? When we do these power calculations, you'll see, I will say, assuming the following things, then with this sample size, we would have 80% power, which really means if I conducted the experiment 5 times, and all the assumptions were always true, 4 of them, I will be able to say, I found it. I would expect 4 of them to tell me I found it. I would expect 1 of them to miss. So it's not guaranteed. If I ran it 100 times, I would expect 80 of them to find it, 20 of them to miss it. That's what 80% power means. Now, as I've grown through the years, it used to be all the power calculations I would write, I would do 80% power. Given up on that, moved it up. Moved it up to 85. Moved it up to 90. Does that increase your sample size? Yes, of course it does. But it also gives you a little bit of breathing room if the assumptions are wrong, which is why I try to do it that way now. Here is the biggest truth. Every power calculation is a guess. It has to be written as a guess. It's not. In fact, if I knew the truth, I wouldn't write the power calculation. Seriously. but it has to be written and explained as this is our best scientific, educated guess. Because that's why we're doing experiments. Okay? Please understand it is always a guess. Please. You must first define the specific game of hypothesis. I can do nothing. I can do nothing, let's put it this way, I can do nothing good. I can do a lot of damage if I misunderstand the design. So the first thing is, bring the specific aims, be ready to sit down, say, hey Dave, we're doing 2 groups. We're going after a diet study. We want to be able to see how much we can change the BMI. All of these things, or whatever it is, no matter how complex it is, that's where we have to begin. You have to help me understand, how are you going to measure your outcomes? Sometimes they're just all, they're what I call stale data. Agree, strongly disagree, all that. If that's the case, I need to understand that. None of that can be overlooked.
Can I ask you a question?
You can always.
On the previous slide, like the previous thought, the 80% power. So if you conduct an experiment and you do the calculation based on 80% power, but you end up enrolling less patients, right?
You're down.
Observation.
Well, you may or may not be down.
So if you still find the result you're looking for, despite having a smaller sample size, does that strengthen your theory? I mean, does that tell you that even though you did not have the power you were going for,
you still detected it? You still declared significant results.
Okay.
And you see, that's why, and can I hold that to the very end, because that kind of takes us down a rabbit trail. Why I don't like reviewers saying after the study's over, hey, what's your power? Either I failed to find it, or I found it. The experiment's over. Power now is off the table. Power is talking about that as we run the experiment, if my assumptions are right, what are the probabilities? Okay? Think of what observed changes association would convince you that the research hypothesis is true. I am going to have to go into a little bit of statistics and throw a little bit of Greek up here in just a minute, but don't worry too much. I'll keep it tame. But as you're considering these things, as you're considering them, that's the time to get to the statistician. As soon as you've got a good idea of all these things, don't wait until much longer. Because the sooner that you can get to the statistician or the methodologist, the sooner, because you know what? Very rarely have I ever done a power calculation and they walked out and they didn't come back to it and say, ooh, we can afford more. Because if you can't afford more, you probably will, and you want the power calculation adjusted. Sometimes they come back and say, David, sorry, there's just no way. There's no way we can get to that sample size after we really looked at the budget. Can you help us? The answer to that is, of course I can. Right? Okay, so let's talk about this. We're going to do a very basic idea. We're one slide away from the money slide. Okay? In anticipation. Keep in mind, and one of the things I will tell you really quick, we've got to be careful. I don't want to run over. That's what I'm thinking. I can teach you everything about a statistical hypothesis test, and you'll never forget it. Because a statistical hypothesis test is nothing more than a jury trial. That's all it is. When we do a jury trial, what is assumed? Which of the 2 hypotheses is assumed? What's the standard assumption when you go to a jury trial? The person is innocent. What's the alternative? What's the second possible outcome? They will say guilty. The way you think of every statistical experiment is you've got to keep in mind, I have 2 hypotheses. One is called the null, which is the innocence in a jury trial. The alternative, what? Why do you go to trial? Because prosecution wants to prove what? Guilt. They don't bring, prosecution will bring somebody in with innocence. If you're trying to prove guilt, well, we're doing the same thing. We're setting up, and we're saying the null hypothesis. always remember, in the null hypothesis, we will have the equal signs. So this is saying there's no difference between the two groups because their means are right on top. They're equal. And then what is key for us is we have to imagine scenarios under the alternative distribution, or the alternative hypothesis. So here, if somebody came to me and said, David, we're going to do a power calculation on two group means, I would say, tell me what's the clinically relevant difference. And then somebody said, well, I really think the baseline group is going to be at 30, or that the control group will stay at 30, but I'm willing to look for a 2.5 difference in the means. This is what I'm setting up, 2.5, that there's a gap between the means. Therefore, I'm hoping this is existing, and that I need to design a study that gives me a good chance to fall on this hypothesis and get off of that. Okay? Now, as we go forward, I want you to think about one more thing. In a jury trial, they present evidence. In a clinical experiment, what's your evidence? What? Don't say the p-value, please. Huh? The data. The data is your evidence, and in a jury trial, there's a special phrase that's used. What is it? Evidence beyond a reasonable doubt. Statisticians that's where that 0.05 number comes from. When statisticians say I'm using a significance level of 0.05, there's my beyond a reasonable doubt. It all lines up, 1 to 1. Okay? So I'm going to run an experiment here. I'm going to have a beyond a reasonable doubt of 0.05. We can debate that in the design. Sometimes you want that lower, sometimes you want that higher. That's for us to discuss and walk through. All right, here's the money slide. Okay, and you're going to say, well, that doesn't look very impressive, but it has everything here about power is here. Okay, so the top one is talking about the shape of the data if the null hypothesis is true, because everything that's centered at 0. Over here, I've shifted it a little bit. I've shifted it actually by 2, not 2.5. Now, depending on when you were trained in statistics, you were either taught the dreaded p-value, or you were taught a concept called rejection region. Understand this, when you're trying to understand power, don't think p-value. Put that aside. Think about rejection regions. And if we did rejection regions, what we do is we carve off little pieces or the tails of the distribution. And what we do is we say, hey, let's put a 5% probability into those two tails. That's where the 0.05 comes from. We want to see something way out here to be convincing, or we need something down here to be convincing. Now, this is the alternative distribution. This is the one that we're hoping is true. What do we hope? We hope it is shifted. But the lines stay constant that you compare to. Those lines stay constant. And so what you're hoping is a lot of this distribution is falling above the green line. Now, how do you control where this distribution falls? By the hypothesized difference. If you hypothesize a big difference between the two groups, you're moving it all the way up here. And if you move it all the way up here, what does your power go to? 1. If all of this distribution was moved above the right green line, then you would have 100% power. Which, when we go to do 80% power, we're trying to find a difference that would shift this distribution up so that 80% of that bell would be above the green line. That's what we're doing. We're trying to find that difference. So there's another magical way that I can make more and more fall within above the green line. What's the other one? We kind of hinted at it earlier. We can shift the location, or I can change the shape. I can always change the shape of the distributions by one key piece. Any indicated yes? How could I change the shape? Specifically, how could I make it tighter? If I could make it tighter, I could make more fall.
Increase sample size.
Increase the sample size. I can always alter the shape by increasing the sample size. So there's your two levers. One, the difference you're looking for, making it bigger would make the power go up. Making it smaller makes power go down. But if I increase sample size, then I'm making things become much more tight, and I have a better ability to see things. Make sense? So I've got two pieces: the clinically relevant difference, and I also have the piece that is controlling shape, which is sample size. All right? And this is true for almost any power calculation we're working with. You go to a complex regression, okay, that's fine. I'm still going to have this basic concept. There's one under the null, there's one under the alternative, and as I move the pieces, I'm altering where they fall relative to each other, and I'm altering the shape of them. And I'm just looking for points, or cut points, or combinations of sample size and clinically relevant differences that achieve a certain level. That's all I'm doing. All right, so I'm going to walk you through one, and I'm going to talk to you about how it needs to be written. Okay, so let's assume that the common standard deviation is 5. Well, let's refresh our memory. What is the standard deviation? Standard deviation is just telling me how much the spread is. I have to have some variability. I'm just picking, and you'll see that sometimes I don't know the standard deviation. That doesn't stop me one bit. Just sail right through it. I'll show you how we can do it. You come to me and say, hey, David, I know there's clinically relevant difference, but I'm not really certain how much variability there's going to be in the data. That's good for me to know. We'll build a very robust calculation, and I'll show you how. We're going to assume that we're going to have a level of beyond a reasonable doubt. Alpha is type 1 error. We say we have to find evidence beyond a 5% probability level. That's what we're doing. And I'm going to do it this way. This happens more times than you know. Hey, David, I got 30. What can I find? What level would have to be, what difference would have to be out there for me to have an 80% chance of detecting it? Sometimes I get examples where the constraints are so tight that they just have to come to me and say, I've got 30. Well, once I'm bound there, I only have one lever to work with, and that's how far apart we move. Okay? So, again, you can go out there. I mean, there are plenty of online power calculators. They're very good. I actually have several thousands of dollars worth of software on my laptop and my desktop to lead me through power calculations. I don't expect you to go spend thousands of dollars. That would be a mistake. We only need one. We can meet together and work it. Why do I show you this? Do I want you to do self-service? No. I don't want you to be afraid of it. I'm not afraid one bit for you to go out there and tinker and come in with an idea of what you think should be going on. That's good. We are at university for a reason. But be careful. Even if you've done it right, you want it written in a specific way that telegraphs every detail. And I'll be very honest, writing a solid power calculation, even for me after all these years, I sit there and spend 30 minutes, 45 minutes for a 4-sentence paragraph, making sure everything is there and they can replicate it. All right? So we would enter the information. We want a difference of 2.5, common standard deviation of 5. We say 30, and the software comes back and boom, 0.4779. What does that mean? How would you explain that? That's, I mean, literally, that's what the computer is going to go back and say, okay, here it is, 0.4779. What does it mean? It means under that assumption, they're trying to tell you 47% of the alternative distribution under this scenario. Because what you just did, sorry to back up, but what you just did is by detailing all these pieces, 2.5, 5, 0.05, and 30, all of these pieces, what you did is you set up enough information to draw out two distributions. That's all you've done. And you're saying there's 47% of that curve within the rejection region. That means 47% or 48% of all the outcomes that you should expect are going to be in a region that can be declared significant. Don't like the word, but that's what is in literature. Okay? So that's going. Now, here we go with the simple writing it up. Notice, you want to know how you can tell that I wrote the power calculation for a grant? Good chance. You ever just start with going online, and we have libraries of really of R01s, R03s, KO awards that we have out there in the CCTS for people just to study, to get a feel for how to develop these things. You see a power calculation that starts with the word assuming, I tell you, because I start every one of them by telegraphing to the whole review section, I'm making some assumptions, assuming the following things. And notice what I said, assuming a two-tailed hypothesis. Go back to the money slide, there are two green lines. Using a type 1 error rate of 0.05. Notice I did not say using a significance level. I did not use beyond a reasonable doubt. I used the statistical term so that people would stop and go, wait, that's only a term of statisticians that use. So there was statisticians looking at this. Common standard deviation of 5. Under all these, I put then a total sample size of 30 per group of 60, but 30 per group provides 47.79% power to detect the difference between two groups' means of this. Everything written out there gives anybody who can get to a piece of statistical software that calculates power should be able to get to that exact same answer. And therefore they have confidence that A, you've reasoned it out right, and that they can replicate it, therefore they're confident in the calculation. Now, is 47.79% good? Would you want to put that out? You're talking about a 50-50 shot. So I would come back and if somebody said, hey David, really, that's the only way, I can't get more than 30, David. Okay. Remember, I have the ability to move things. These are all assumptions. So what do? Somebody comes back and says, okay, where's the cut point for 80% power? Okay, here we go. I can reverse the calculations, start them over, and say, okay, now if you want 80%, but you're stuck at 60, assuming a two-tailed hypothesis test, using a type 1 error rate of 0.05 and a common standard deviation of 5, total sample size of 60, everything has stayed the same, except now I say 80% power to detect the difference between two group means of, and this had to move. I had to spread them further apart. By spreading them further apart, I have pulled those two distributions apart even further so that you would have 80% of the alternative distribution above a green line. That's all I've done. So here you're looking at, you really need probably right at let's just round it, let's say 3.7. You need a difference in means of 3.7 to get up to 80% power. These are the type of discussions you would expect to have with statisticians, going back and forth. Now, yes, ma'am? Go ahead, raise your hand. Go!
So all you're showing are normally distributed populations. Is that what for non-normally distributed observation also?
The answer to that question is the concepts hold true across all statistical tests. What I'm bringing you is the most simple of the ones for the normal distribution. But across all statistical procedures, when we're talking about powers, you can stop and imagine there's one distribution or one shape governing the outcomes. If the null is true, then when I write my assumptions, I get another distribution, and as long as I know where those cut points are, I can manipulate the second to find 80% power, 85%. It's true regardless of the statistical test. Now, that's a very bold statement. We say the common statistical test. There are certain things out there that are so new, we don't have formulas for them. We can still get power calculations based on simulation, but I would say 95% of all the stuff that comes in, I can show you what's going on in the model, draw you a picture of what's going on under your assumptions, give you those cut points. So yes, it's a generalizable concept. Okay, what was the other lever? Suppose all of a sudden, I don't know, somebody came in and said, I'll give you as much money as you need, get whatever sample size you want to find 2.5. So we could put the flag down and say, I've got to have 2.5, then I have to move the other lever. And that's not too hard either, so I can do that also. I can come in and say, everything stays the same, but this time I move the sample size again. 128 would give me 80% power to detect the difference between those two, or those two things. Okay? Any questions at this point?
So if you keep 80% of power, just thinking about the review, so that's the
That would be the, I have had grants, that's a great question. The question was, is 80% the minimum power level to convince a study section? The answer is, in my experience, I've gotten it by with 75. Okay, but I generally start guiding people at 80%, but you'll see in a minute, I actually have given up on writing the one paragraph. I actually give you a table, and I will say, here are a series of assumptions on the rows, assumptions on the columns, and it shows a bigger landscape. And that is very helpful to reviewers, so they can see that over a wide landscape, we would maintain 85% power or 90% power. Okay? Okay, let's go over proportions, and then don't let me forget to circle back to the question about when reviewers come back and say, well, what was your power? And specifically journal reviewers. Okay? Don't let me forget that. All right, now we're going to make it a little bit easier. And, all right, so let me ask you something. I just said to you, I have a big sigh of relief when people call me and say, hey, I need to do a power calculation that's 2 proportions. It's really easy because in a lot of ways there's a lot less assumptions. However, it's never good for you to call and say, I'm doing proportions. Your sample size is going to be higher. It's just that easy. Sample size is going to be higher than you could measure something continuous. You can measure something continuous and try to get there for the sake of having a smaller sample size. So when I say proportion, keep in mind we're looking at, are you hypertensive, yes or no? The yes or no type. These are easier. Why is it easier? Because of the way, this is why people go study and get PhDs in statistics. Because you've shifted the distribution. You're not talking about the normal. When you talk about the normal, you've got to talk about 2 things. You've got to talk about where the center is, that's mu, the Greek letter mu. And then you got to talk about the spread, the sigma, the standard deviation. So you talk about the median and the standard deviation. When you go to proportions, You just got to tell me what's your expected proportion, because I can derive everything else I need out of that one number. It's a nice luxury. But if you came to me and said, hey, I'm expecting a proportion of 0.5, I can get to the standard deviation. Don't even discuss it with me. You've already restricted me. I know what it has to be. Okay? So the main thing is for you stating the proportions provides me all the information I would ever need. And from that point, now keep in mind, how are you going to increase power for proportions? Talk about that to me for 1 second. Right? 2 levers at all times. What are those 2 levers? How far I push those proportions away from each other, as well as sample size. Okay? So here we go. Now understand something. I do want to emphasize this. Again, I'm not going to go back to the money slide. It's still the same money slide. But think about this. Or just take 1 minute. I can shut up for 1 minute. It'll be hard, but I will. Okay? Why did I set the 2 of them equal there? Why did I set the 2 proportions here as not equal? Now here you go seeing a statistician again, the fingerprints of a statistician, that I've used pi instead of mu. Pi telegraphs. We're dealing with proportions. So, but why is this set equal, and why is that set not equal? Exactly. Under the null says, okay, they are going to be equal, so I must make the null true, so I pick 2 proportions that are set to be equal. But I have to pick another set that would make the alternative true. So I just arbitrarily picked 0.2 and 0.30. I could have just as easily picked 0.2 and 0.25. I could have just as easily put 0.2 and 0.20001. Why am I giving these examples? Right. Speak up. So there are people in line. That's exactly right. By picking all those different examples, I'm picking different distributions under the alternative. Now think about my examples. I did first 0.20 and 0.30. That's a pretty good gap, right? Right? The second one I gave you was 0.20 to 0.25. I closed the gap. What's going to happen for a fixed sample size? If I'm closing the gap and I have a fixed sample size, what has to happen to power? Going down. And then think about that. When I did my last example, it was 0.20 versus 0.20001. Well, the alternative is true. They're not quite equal. But you've got to know you have no power for that. And if you ever want to design a study that takes such a small difference, you're going to have a sample size out the roof. You've got all concepts of power. You can think about it in those terms. Because what are you doing? As I kept decreasing the sample size, the gap, as I closed the gap, I kept moving the distribution back closer and closer. The alternative distribution became much more like that which I was imagining under the model. And here, look at this. The sample size is 588 total. Good size sample, a very good size study, and therefore you would have to be one of those situations where you're going to have, a research staff. You're going to have a lot of people working towards you managing and collecting that data. Okay. Now this is the other thing. This is where I have evolved to over the years. A lot of times you come to me and you go, David, I'm really not certain of what my variability is. I'm going to go back to the example where we're talking about means, where you've got to talking about how far apart are the means, and you've got to figure out something about the spread. David, I just don't know. I've gone through the journals, I've gone through the literature. Some people are showing me a standard deviation of 2.5. Some people run this experiment. Sometimes they get a standard deviation of all the way up to 7.5. No problem. We can deal with that. And what I will come in and do is I'll come in and say, for a fixed sample size, suppose you say, hey, I can afford, there's a lot of information hiding in this table. I can afford, let's just say hypothetically, you can afford, okay, you can afford 60 individuals. I had to look at the table to remember and deduce exactly which one I had to put in. Suppose you can afford 60 individuals, 30 into each arm. Look at what this table is telling you, that if you have a small difference, clinically relevant difference, matched with a small sigma, what do you get? You get very high power. So you could find a small difference if you're lucky enough to have a tight distribution of outcomes. But what happens if you're really looking for 2.5, but you're starting to get more and more variability in your data? What happens to your power? It starts going down. And this is why in most studies, when we're 30% into data collection, I don't go look for the difference. That's a no-no. But I do go look to see what the variability is. Because if I was way off, I need to talk to the investigators quick. If we're way off, we may have to ramp our sample size up. Or sometimes I've been lucky enough to go the other way. If we thought it was going to be really noisy, it's not noisy. It's really tight. So we're in a really good situation. Okay? Then what happens here as I move and start imagining I want a bigger difference between the two groups? What's going to happen to power? What should be true about column 2 as compared to column 1? You can look at it. What is it? As you get a bigger gap, regardless of what your variability is, if you hypothesize a bigger gap, what happens to power? 99%, 76%, 42%, these are all increasing. Okay? And suppose even within A and go across a row. Suppose that you said, okay, I'm pretty confident it's 5. Okay, I'm pretty confident it's 5. Variability sigma is 5. Then you know as you move across and continue to increase the distance between the means, you're pulling the alternative distribution, more and more of it, up above the significance level defined by that green line. That's what power is, okay? So I always like to give those tables, and what I'll do in a grant application now, I will pick the one that the clinicians really believe that they won't go after, for example, the 92%, but then I will explain how the table helps people understand. Because in this situation, we have a reasonably good ability, not even sometimes highlight and bold the areas that we really believe will be, and show that across that all those possibilities, we've maintained adequate power. All right? It's okay to build a table and present multiple power calculations. I actually find that helps a lot of people, a lot of reviewers, to get beyond criticizing the power calculation. All right? Okay, again, why it's not the most important piece. And understand the calculation itself is not the most important piece. The most important piece is giving the details to allow the replication. Okay, grant is one or loss on a specific damage stage. Please never forget that. I'll tell you again. I have yet, we're still striving for it, but I have yet to get the NIH style review that says these aims are horrible. But boy, that was a great power calculation, a great analysis plan, let's give them the money. It doesn't happen. Okay, so start there. Always emphasize there. Once you've got your outcomes set up, bring it. Once you've got your design, kind of envision, it doesn't have to be finalized. Envision. It's time to start talking about sample size and power. Understand, I spend a lot of time on the phone with NIH. Study sessions. Why? Because they're asking me, can I replicate it? Can I, just by what's written in the paragraph, sit down with a cup of coffee, turn the computer on, and show that exact same calculation? Makes them feel a lot better when I say, yes, I can do it. Makes them feel a lot worse when I say, hey, There's not, and usually you'll see this, there is not sufficient details provided to allow replication of this calculation. Okay? You want to be able to have it written in a way that people, and you're saying to me, well, David, I have done this. You said sometimes it gets really complicated and you've got to do it by turning the computer on and telling the computer to do the hypothetical experiment 10,000 times. Yeah, I've done that. I've used that as a power calculation and I've gotten it funded. How in the world did you get it replicated? How could you, they can't replicate that. No, but I put the power, I put the software in the appendix. I wrote the whole, I gave them the whole program and said, if you have any questions, here's how it's done. Got it. Right? Even if you're, yes?
So just that comment depends on the software which you, there could be few differences.
There can be a few differences, yes, and understand, doing, especially if you're going to, if you hear the statistician say, I've got to do it by simulation, there has to be a little bit of extra care. And by that, you need to be able to say, I need the program written in a way that it can't be reproducible. Okay? In other words, you've got to be able to set certain characteristics in the program that guarantee the same numbers will be produced over and over. Always, even if you have done, even if, and again, I'm quite confident that almost everybody in the room, if they really sat down with the software, would come to the correct power or sample size. Well, that's still not a reason to skip meeting with the methodologies. Just to be able to sit down and have somebody, you can say that you may not believe this, I am the chair of biostats. Before a grant goes out, I'll email the power calculation to 2 or 3 of my very good friends. Okay, prove it. Look at it. Is there anything missing? Is it clear? Recommend that you always have another methodologist look at. Okay? Keep in mind the bird clinics are always open. We have walk-in biostats clinics. I want to clarify something. Just because it's called a clinic doesn't mean anything's wrong. Okay? It's not like you're sick or anything. We just mean you can come in and get advice. Talk about the fundamentals of analyses. A lot of times, y'all can laugh at me. It's true though. I've had people come in and say, David, they like the paper, but they're not convinced of certain things. How can you help us address these statistical concerns? I said, add a graph. We just put in a simple graph. We add one graph of paper, it sails right through it. It shows all the information they need. A picture is worth 1,000 words sometimes. And so it's a lot of times we're just doing graph development. We're doing power calculations for either manuscripts or grant submissions. Now let's pause right here and let me go down the rabbit trail. When reviewers come back and say, okay, you rejected and you have concluded that there is a significant result, what was your policy? That is a very difficult thing to address for a journal review. Because a statistician would say, it's irrelevant, we've already rejected. Our power is 1. We rejected. We've done it, game over. Do we have significant results? Whether or not we've either found true results or we made a type 1 error. One of those two. So to talk about power now is kind of muddying the waters. Reviewers don't like it when they talk about approach. They think you're being argumentative. They think that you're dodging them. So what I will carefully do is I'll come back, and there's nothing to stop me from saying, based on what we've observed in the experiment, this is what, if we had to do it again, we would anticipate X% problems. Answer that. Okay, but I don't think that's a solid question. It is a better question when you have failed to declare something significant. You're trying to publish a non-significant result. Yeah, I do that too. I've had to publish non-significant results. But at that point, the question becomes, were you underpowered? That's a reasonable question. Or were your assumptions grossly wrong? That's a reasonable question. But it's never a reasonable question after you found it. I'm always going to want you to ask about how at that point. Okay? The other thing about the walking point, the other thing is you can go to the Research Commons and email the CCTS and say, hey, I would really like a one-on-one consultation. You know, I could get some ideas with regard to the walking in, but I really have I have a K award, or I have an R that's going, or I have a pilot. I really would like to get one-on-one time with a methodologist. Email, we have done all styles of NIH. We've done Department of Defense, NSF, National Science Foundation. No, NSF is not stand for not sufficient funds. It is actually the National Science Foundation. So we do all of those, happy to help out. Like I've said before, I am a firm believer in collaboration. Okay, now here's the sales pitch. What is collaboration? Collaboration was defined in 1989 in Barbara Gray's textbook on collaboration as when individuals come together from very different backgrounds in an environment of mutual respect to solve a problem beyond what could be achieved in isolation. So I want to bring my skills in with your skills to get the best we can out of it. If you ever have questions or you need a consult, it's there on the webpage, and email in, and more than likely it'll come to me, and then I'll try to pair up very carefully the correct methodologist to your needs. Okay? And with that, I'll take questions. Questions?
You said twice per week.
Hmm?
The second, last location. Yeah, where is the location?
Here,
Oh.
in this room, on Wednesdays from 11 to 1, and then the Edge of Chaos, which is over in Lister Hill. There's another clinic, so those are, the Wednesday clinics are in here, and the Monday clinics are over in the Edge of Chaos, and they run from like 10 to 2. Okay? Other questions? I will.
Can you help with the study design?
Yes. Yeah. With regard to what we believe is the best way to design it, yes, of course we can. Other questions? All right, thank you. Well, I've got to, another round, I've got to bring back to Cobalt.
Just want to say thank you for your nice, clear explanation, and I think it helps with both you as well as participants.
Well, the next one, same idea. Okay.